So good morning, everybody, and welcome to this new webinar from the Spanish Specialized Group of Crystallography. And I am very pleased today to introduce our speaker, Professor Pierangelo Metrangolo. He's full professor at the Politecnico di Milano. He did his PhD in Milan also, and he's also related to other institutions in Europe, because he also holds a position as visiting professor at the VTT Technical Research Center of Finland and in the Center of Excellence in Molecular Engineering of Biosynthetic Hybrid Materials of Aalto University in Finland also, where he's also chairing the local node of the UNESCO Unit Twin Chair Greennomics. He has done a pioneering work on halogen bonding, initially more focused towards crystal engineering and developing functional supramolecular material, and later on has focused more towards the relevance of halogen bonds in biological systems. And in fact, he achieved a ERC grant aimed at investigating the relevance of biomolecular halogen bonds. In those areas, have published nearly 300 papers, and he has received a remarkable amount of awards. Amongst them, I would like to point out that he received in 2019 the award of Fluorous Technology. He has also received earlier on in 2009 the UPAC Young Chemist Award, and also the Crystal Edgecombe Lectureship. He has also received a recognition from the Division of the Organic Chemistry of the Italian Chemical Society and the Journals Grant Award of the Royal Society of Chemistry. As well, he has received awards in innovation, such as the Switch to Product Innovation Challenge of the Politecnico di Milano. And he also is involved in several editorial boards, such as Crystal Edgecombe or the Crystal Growth Desk, Crystal Growth and Design from the ACS, and he's currently Vice President and President-elect of the Physical and Biophysical Chemistry Division of the EUPAC. So I think it's a great honor to have him today to tell us his recent advances in halogen bonding. So we are really looking forward listening to his talk. So please, the screen is yours.
Thank you, Marta. Thank you for the invitation. It's a great pleasure to speak today to you, although I would have preferred to come in person to Spain, which is one of my most favorite countries worldwide. Anyway, maybe next time. So it's a great pleasure, and good morning, everybody. I now try to share my presentation mode. Okay, it should be fine. In the next time, I'll try to bring you maybe in this new word for you, which is the word of halogen bonding. So first of all, this is me, actually. I'm a chemist. I usually try to make experiments in the lab whenever possible. This, as you can see, is a crystallization in my 9-year-old son. And I make some recognition, some receptors, not much about uranium, but yes, nowadays we are introducing biomolecules like, for example, DNA. And but this day, the topic is about halogen bonding, and actually we worked with the UPAC a lot to get an accepted definition. And this is the definition of the halogen bonding according to a UPAC, which is the interaction between an halogen working as the electrophile with a nucleophile. And this new definition is nowadays very much accepted. It comes from the fact that halogen atoms are pretty much polarizable. Therefore, when halogen atoms are bound to electron withdrawing residues, like for example, the fluoromethyl group, especially with the heaviest one, a positive sigma hole, which is electron deficiency, occurs along the extension of the carbon iodine bond here, also on top of bromine and also with chlorine. And but actually we were not the first studying halogen bonding, because the very first example of a halogen bonded complex was reported by Guthrie in 1863 with the composition one equivalent on ammonia plus one equivalent of molecular iodine. And it was definitely Odd Hassel in his Nobel lecture in 1970, which reported a lot of different halogen bonded structures, for example, between dioxane and molecular bromine, or benzene and bromine. But the very first use of the term halogen bonding we could only find in the literature was given by Zingaro and Hedges in this paper, 1961. And after, in a very important review by Dumas, Gommel, and Guérin, it was then mentioned many times in this Patai series. So I wanted also to acknowledge many other different contributions who made the history of halogen bonding, like, for example, Tony Ligon, who reported several interhalides complexes with double and triple bonds in the vibrational spectroscopy, but also Bader with the crystal structure of molecular fluorine. And as you can see, even fluorine is making halogen bonds where the positive side of one fluorine atom is pointing to the negative side of another fluorine atom in the crystal structure. And last but not least, Gautam Desiraju studying type 1 and type 2 halogen bonds or intermolecular interhalogen interaction, which were recognized in the case of the type 2 being truly genuine halogen bonding. This was recognized much later on. So our first experiment on halogen bonding was this one, which is very nice, but I need to switch the pointer to this one. So this is a video. I hope that the video starts. But yes, as you can see, it's a very trivial nowadays experiment where you mix a diodo tetrafluoroethane with this diamine. So the amine is in the vial, the diodo tetrafluoro is in the needle, and as you can see, the two compounds already from the gas phase mix, forming very beautiful single crystals melting at more than 100 degrees. And this was our first halogen bonded co-crystal, where, as you can see, two liquids form a high melting solid by just interacting through halogen bonding. And this is nowadays we are using for teaching students what supramolecular chemistry is and halogen bonding is, because it's a very, very easy and astonishing experiment. So later on, we wanted to try to compare the halogen bond with the most known hydrogen bond, and therefore we did some, I would say, simple crystallization, competing two halogen bonded species with one hydrogen bond donor, like hydroquinone, and we were only having the halogen bonded co-crystalline solution, also in the aliphatic series. And also in 2017, Lee Brammer, Robin Perutz, and Chris Hunter made the same experiments, and luckily they got to the same results. And but not only fluorinated compounds can behave as halogen bond donor, because even without fluorine, the iodine, when polarized by the triple bonds, for example, is a very strong halogen bond donor. But even diodobenzene, which is a very common molecule in organic chemistry, it has a halogen bond donor iodine. So nowadays we can see that halogen bonding is considered one of the tools for assembling molecules into supramolecules, and this tool is very similar to the most known hydrogen bonding. The new knowledge about halogen bonding also is making a very established mechanism to be revised. For example, the nucleophilic substitution can be seen at a certain point, even as a halogen bonded complex, for example, in its front side complex. So many people are happy with this nomenclature and started working in the field. So we published the first book in 2008 and 2 books in 2015 with many different contributions from many different people. And now the field is growing very fast. And for example, publications in 2021 are even more than 2019. Many new players are coming into the field, and moreover, the nomenclature of halogen bonding is very much accepted. So people are publishing from UK, Finland, China, US, and also main player in the field are obviously from Milan, but also from Oxford, from Germany, from Spain, and from Russia and Finland. Main journals are the crystal engineering journals, but not only, we have also some more generalist journals like JAX and Angevante Chemie. And also we wanted to create the first ever symposium on halogen bonding, and we made it in my hometown nearby Lecce. This is my summer place house here behind this tower in Porto Rosario 2014. We were many, around 200 people there. And then 2 years later in Gothenburg, then in the US, then unfortunately Stellenbosch in South Africa had to go virtual with more than 250 participants, but we are really waiting for next edition this year in November in Japan, where you are also invited to join. So we have used halogen bonding to make crystal structures, but always looking for a function. So we went from polymer self-assembly to photoresponsive materials or cage-like structure of the Fujita type, an ion transporter, dynamically porous materials, and also molecular liquid crystals. And so the reason why I really like halogen bonding is because of its directionality, since the halogen bonding always occurs along the extension of the carbon halogen bond to an angle which is very close to 180 degrees. It can be easily tuned by reducing the size of the halogen atom from iodine to chlorine, and moreover, the halogen bond doesn't suffer the competition of water. It can be easily also done in water. So the directionality is very high, which means that you can plan your co-crystals, making, for example, linear chains, or if the halogen bond donor moieties are at 120 degrees, then you make zigzags, or even narrower zigzags if the 2 halogen atoms are at 60 degrees. And this gives you a very high planning on your crystal engineered structure. For example, you can plan to make honeycomb-like structures like we made with this 3-iodo trifluorobenzene, where the cation is entrapped inside the honeycomb-like structure. Moreover, we wanted to challenge our planning with a very complex topology, and this is the Borromean rings, where you have 2 circles which are parallel each other, and it is only the third which tightens all of them together. So we wanted to replicate this topology in crystal structures. Therefore, we took a naked I- coordinating 3 different iodoperfluoroalkane we got very large and corrugated honeycomb-like structure, which not surprisingly interpenetrated by Borromean rings. And the reliability was so high, which we can also use different building blocks, for example, diode-octane and diode-hexanes, getting always the same Borromean-like structures. And moreover, this interaction is so reliable in this system where you can change from I- to bromide and chloride, or from potassium to sodium, ammonium, rubidium, changing from diode-octane to diode-hexane, getting 15 Borromean ring structure out of 24 co-crystals, due to the very reliability and directionality and strength of these halogen bonds. Moreover, we were looking whether we could isolate also the non-interpenetrated polymorph, and actually we were able to do that by simply changing from ethanol to methanol the crystallization conditions, and we are always getting the same honeycomb-like structures, which only in the case of the ethanol co-crystal were interpenetrated. And we could characterize that these two are polymorphs where the non-interpenetrated system converts upon melting into the Borromean interpenetrated system. And this was very nice because actually we wanted to see whether this very complex Borromean structure forms fully in the solid state. So we made these experiments with a ball jar, with a jar and a ball milling under the synchrotron radiation, and we could discover a very nice story. Actually, this three-component system in the solid state might come and get to the interpenetrated system or to the non-interpenetrated one. And actually, if we use only two small balls, it is very easy to see here that actually you get to the non-interpenetrated system in a very high yield, directly in the solid state. But if you, obviously we were able also to report the intermediate that we were getting, which is a neutral co-crystal where the cryptofix is coordinating the diodoperfluoroalkane, but this intermediate disappear very soon in order to get the three-component system. But if you mix the two components in a ball miller using a single bore with much more energy, the intermediate soon, very, very fast, converts to the Borromean ring structure. So it is surprising to me to see that this very complex topology can be obtained also directly into the solid state, and we can control obtainment of one polymorph or the other polymorph simply changing the milling conditions. Okay, good. So let's turn now a little bit to more biological system, because there are many halogenated compounds in biology. And for example, we have fluorinated compounds, which are very important drugs, but there are also some chlorinated natural compounds and some other chemicals which are very much industrially used. For example, this decabromodiphenyl ether is a flame retardant. This PBDE73 is also another flame retardant. And you can recognize that these two compounds are extremely similar. And this T4 is our thyroxine, which is the thyroid hormone in our body. And actually, the two compounds behave similarly. And this pollutant is able to disrupt our thyroid hormone system due to the same interactions. So we wanted to study this. Obviously, there was already some literature where demonstrating that the thyroid hormones binds to the receptor thanks to halogen bonds, but we wanted to study the behavior of these pollutants. So starting from 2012, thanks to this ERC project, I try to introduce halogen atoms into amino acid, peptides and proteins to get new functions and new structures. And the reason why I wanted to do that is because whenever we are stressed, so we are producing hydrogen peroxide with chloride and bromide, we make reactions on our amino acid, halogenating our proteins, and actually bromotyrosines and chlorotyrosines are very well known biomarker of oxidative stress in many diseases. But nobody knew about the mechanism why a protein which is halogenated doesn't work anymore. And we actually proposed that once the protein is halogenated, it misfolds to accomplish new interactions. So we wanted to demonstrate this, and the first way to demonstrate this is to look into the interaction between pollutant molecules and biomolecules. This is a series of the bisphenol A tetrahalogenated. These are very well-known industrial molecules and pollutants. We reported the single crystal structure where you can see that the sigma hole of the iodine is looking for electron density on the tyrosine ring. And finally, we were able to crystallize a wool, this is a single crystal structure, a wool recombinant antibody binding thyroxine. And as you can see, thyroxine is bound to the antibody thanks to halogen bonds, sulfur to iodine, and the same iodine-tyrosine interaction that we saw in the homocrystal. And this was quite nice because we could also crystallize the bisphenol A tetraiodinated with the same antibody. And we were using also these antibodies to make some sensors which were able to recognize thyroxine at a picomolar concentration and the pollutants at a nanomolar concentration. So also, we wanted to study the interaction of the halogen bonds with the peptides, and moreover, we studied for this reason this very, very simple model system where you have a model of the beta sheet due to this N-methylacetamide, which also make co-crystal with different iodo-tetrafluoro-pentafluorobenzenes. So this is the hydrogen bonded chain of the N-methylacetamide, and actually these hydrogen bonded chains interact in a perpendicular manner with the halogen bonded species thanks to halogen bonds, as you can see here. So actually the halogen bonds can interact with the beta sheets without disrupting them. This was the basic idea. Therefore, we took a very well-known peptide able to make amyloid fibrils. So we functionalized the phenylalanine groups with iodine and bromine in two different positions. We were lucky enough to get single crystals of these iodinated peptides because halogenation here is improving the crystallinity, and it's not easy, as you may know, to get the single crystal structure of amyloid peptides. We have nowadays a lot of those structures. And actually, we could study the fibrillation of those peptides which are now halogenated. And as you can see, all the halogenated peptides were able to make hydrogels where the wild type didn't do anything. And simply replacing one hydrogen atom with one iodine atom in position number 2 got us to a very strong hydrogelators where only 0.2% of the peptide was able to make very strong hydrogels. The gels were incredibly strong, and also the gel transition temperature and the elastic moduli are decreasing with the polarizability of the halogen atom, and the complexity of the fibrils is also dependent on the halogen atom, and this is the bis-iodo peptide, where, as you can see, we have a very mature helices, which are quite unusual for so a small pentapeptide. This is a microscopy images of the peptides where you can clearly see the very big helices. And obviously we could not see high resolution structures of these fibrils. So there are several possibilities for halogen bonding there. But we believe that the most suitable is this one, because from the spectroscopy, we see the changing in the stretching of the carbon iodine bond in the Raman, coupled with the IR change into the peptide bond. So we believe that this is the kind of interaction occurring and responsible for this improved fibrillation. So, but we were not happy with that. We wanted to have a clearer evidence. Therefore, we synthesized this peptide, which is now tetrafluorinated. And now this halogen bond donor is much more strong. But this synthesizing this molecule was a nightmare. It took 1 year, 5 different people, and only one lady, Luisa Lasciarfari, was able now to synthesize this, and now we have scaled this up to 5 grams in one single batch. So obviously now this iodo tetrafluorophenylalanine is a very strong halogen bond donor. It is soluble in aqua, in some water, sorry. You can make organocatalysis in this kind of reaction of condensation, where you can see that this peptide is making this small amino acid is making halogen bonds with itself and the substrate. So we also crystallized this amino acid with N-methylacetamide, and we could discover that this halogen bond donor makes very strong halogen bonds, as you can see, 20% reduction of the sum of the van der Waals radii. So we took this fluorinated peptide amino acid back to the full peptide, getting much stronger gel compared to the former one, and much more complex helices, where you can see that this tetrafluoroiodo peptide makes very complex amyloid fibrils already in 50 micromolar concentration in water, and these helices are able to make even more complex structures like double helices, triple helices, and even more complex ones. So we wanted to understand a little bit more the binding, therefore we had to rely to computational methods. This is the hydrophobic pocket, which we are going to modify by halogen bonding. So we calculated obviously the sigma hole on top of the iodotetrafluorobenzene molecule and took back this as an extra particle into the full fibril, which is made of 240 monomers, and obviously a lot of different possibility arise for halogen bonding, where, for example, in the formerly hydrophobic pocket, now we have a fully open hydrophilic pocket where the iodotetrafluor is binding the oxygen of the aspartate and the asparagine. So not surprisingly, this formerly hydrophobic pocket becomes polar and hydrophilic, and obviously there are a lot of water molecules inside the pocket. So the concept is general. So we applied this to another peptide, which is the KLVFF, another amyloidogenic peptide, where we could substitute to phenylalanine with different halogen atoms in different positions, and we're always getting nanostructures. As you can see, we were getting nanoparticles in one case, fibrils in another case, ribbons, or very complex hairy particle. Only with the bromobenzene, which is the weakest halogen bond, we only got a very amorphous structure. And moreover, unfortunately here, for somehow reason, the crystal structure is not displaying, but in this paper, we were lucky enough to crystallize for the first time these peptides, and we could see in the high resolution single crystal structure that the halogen bonding is cross-linking the beta sheet by making an orthogonal halogen bonds with the beta sheets. Okay, introducing halogen atoms into peptides also make you to introduce new functions. For example, we use these diodo peptides for mixing these peptides with gold, and actually without any iodine, no reaction occurs. Whenever with iodine, by simply mixing one equivalent of gold chloride plus one equivalent of the peptide, heating 60 degrees for half an hour, get you to these purple solutions, where if you look inside with a microscope, you see very complex objects. In this case, we have roughly 50 nanometers supraparticles, which are made of peptides inside, fully decorated by gold nanoparticles on top. And surprisingly, these very complex objects, they just self-assemble themselves in solution. You mix the two compounds in water, warm it up to 60 degrees for half an hour, and what you get are these very beautiful objects, where inside there is the peptide, and there is a video again here, and you can see here the 3D reconstruction. Inside, basically, there is only organic matter. Outside, this self-decorates with gold nanoparticles, and since the gold nanoparticles are on top of a chiral peptide, then you can see a chiroptical signal in the visible light. So it took some time to understand the mechanism, but actually we were quite happy because we understood that actually the presence of iodine starts the reduction of gold in a very, very complex system, which first self-assemble and then make the reaction of reduction. You can see more details in the paper, but obviously this was general because also other different peptides can be self-decorated by the gold nanoparticles directly in situ. So moving from beta sheets to alpha helices, we wanted to use halogen bonding to make peptide self-assembly, and we got this 32 amino acid alpha helix, where we could replace an alanine in position number 16 with tyrosine. And tyrosine is making a hydrogen bond here, promoting the self-assembly from a dimer into a trimer. So it is possible by introducing a hydrogen bond donor, converting a self-assembling dimer into a trimer. We made it with tyrosine, but we wanted to make it also with the halogen bonds. So we replaced the same alanine in 16 with our iodotetrafluorophenyl group here, and we got the single crystal structure of a trimer, where we could see actually the halogen bonds in action. And not surprisingly, the energy of the two systems, the hydrogen bonded one and the halogen bonded one, are exactly the same. So this is going to be out very soon in biochemistry. So moving to understanding of some pathologies, for example, in the case of Alzheimer, we studied this other structure. This is this sequence is the initial part of the beta amyloid, which is responsible of the Alzheimer's disease. And actually, when you modify the tyrosine with 2 bromine group, which might happen in vivo also, you get enhanced fibrillation. We were lucky to have the crystal structure where we can see the halogen bonds and also an augmented fibrillation due to the halogenation. So actually, we believe that one of the initial steps of the Alzheimer's disease can be halogenation through oxidation of these tyrosine groups, and this becomes to be more fibrillating. Finally, I wanted to show another system where we are taking inspiration from nature, studying this protein. This protein is called resilin. Resilin is the most elastomeric protein in nature. And we only considered a very small heptapeptide, SDS-Y-gap. We modified the 2 hydrogen position on the tyrosine group with 2 bromine atoms, and we got highly resilient fibrils. So actually, with a very small heptapeptide, by halogenation, we could have elastomeric properties in this peptide resembling those of the full protein, which is 600 amino acid. So the peptide is totally biocompatible. With this system, we got another ERC grant, and we patented that, and also won the Innovation Challenge competition at our university to bring this peptide into the market as a new bioelastomer. So we are working a lot with this peptide, which is very good in giving elastomeric properties to any kind of material. Finally, I wanted to say that there are several other interactions to be discovered in the databases. And for example, with this paper, we demonstrated that actually chalcogen bonds occur very commonly in the protein data bank of selenoprotein. As you can see, directionality is very, very clear. So with the structure of selenoproteins, which are many in the protein data bank, we could also recognize that biological chalcogen bonds are also very much directional. So in the last few minutes, since I know that you like very complex crystal structure, I wanted to change a little bit from the heavier halogen atoms to the lighter ones. Obviously, the lightest one is fluorine. So we have an active research line in fluorine with this molecule Perfecta, which is a very good contrast agent for 19-fluorine MRI. And we are working a lot in nanomedicine with this molecule, but I don't have the time to show this research line. I simply wanted to say that we were able to functionalize this molecule with the thiol group. So this is the thiol molecule. As you can see, the single crystal structure is there. We made, through the Brust method, nanoclusters, and we were lucky enough to get the single crystal structure of this gold nanocluster. So this gold nanocluster is made of 25 gold atoms. This is the core of the gold atoms. But since every single ligand brings 27 fluorine atoms, the total amount of the 18 ligands of fluorine atom is almost 500. So this is a 20 kilodalton gold cluster, and as far as we know, is the most fluorinated nano-object ever described in the literature. So this is now under press in Nature.com, and will come out very soon. But since I know that you like crystal structure, this is a quite complex single nano-object which crystallizes with a lot of fluorine-fluorine interaction, which we were able to demonstrate, that are attractive in getting and stabilizing this single crystal structure. So actually, the crystals of these compounds, of this cluster, are extremely beautiful. There is also a nice story to tell about this, but maybe I should tell this in another lecture, another time. So it's now time to go to the conclusion. So, you know, halogen bonding is nowadays used in many different research fields. We just published also a highlight paper about the use of halogen bonding controlling optoelectronic properties of perovskites, but I wanted to focus in my last years in research about the biomolecular implication of halogen bonding. It's a very, very multidisciplinary research. Therefore, I need to thank all the different collaborators in many different countries, all the funding agency, and obviously my research group at MyPolyMe, the non-permanent staff, the permanent staff, and people in other departments. And I only wanted to say that this was the last Congress that I organized in person. It was in 2019, summertime in Lecce, my hometown. It was a beautiful 800 people conference about supramolecular chemistry. I truly hope that we will be able very soon to get back to in-person meeting. So that's it. This is what I wanted to tell you. Again, thanks Marta and all for the hospitality, and I'm very open to any kind of question.
Okay, so thank you very much. It's been like a really, really nice talk to see all the potential and the different aspects of the halogen bonding. And now we are open for questions that they can be sent to the chat. And while we are waiting a little bit for the questions, I was wondering, because you are doing mainly using iodine for the functionalization of these amino acids. So do you expect to have the same result with a bromine, or like which one will be the difference of having the bromine instead of iodine in these halogenated amino acids and peptides?
Okay, so obviously, since the halogen bond strength decreases with the halogenated polarizability, obviously iodine is usually a better donor. But with the tyrosine peptides, we are only using bromine because bromine is more biocompatible and biomimetic. So actually we see the same effect. So it's a bit weaker, but we clearly see that in any case, the halogen bond with bromine or iodine, even with chlorine, is reinforcing the beta sheet. Obviously, the beta sheet is the strongest interaction, but the halogen bond is interacting with the beta sheet. So in the system of the model with the N-methylacetamide, we have 3 crystal structures with bromopentafluorobenzene. So definitely bromine is also good.
Yeah, so basically it's going to be similar, but sometimes less strong. Like exactly. You were mentioning with the amyloid self-assembly, I think, like with bromide, you were getting more amorphous structure because of having this.
Yeah, but
it's a different effect.
Yes, but please remember that amorphous structure was in solution.
Ah, okay. Okay.
So it wasn't able to build up a nanostructure in solution. But if you crystallize, for example, this is the picture I couldn't see in before. So this is the KLVFF, which is iodinated. And you can clearly see beta sheet interdigitation, and the halogen bond between iodine and oxygen is cross-linked in the beta sheet. So we have the crystal structure in this paper also with the bromobenzene, and we are getting exactly the same structure, where the halogen bond with bromine is still there, obviously a bit weaker.
Yes, I see. Yes. And also it was very interesting the another curiosity that I have is like beforehand you showed the influence of these chlorinated compounds in the stress, like, and you mentioned mainly chlorine and bromide, and
Yes.
they are, so then naturally do we get these derivatives due to stress that they are iodinated, or is only bromide and chloride?
It is
systems.
no. The only biomolecular system where we have iodine is our thyroid hormones. But bromination and chlorination is the second most known oxidative stress related mechanism. Actually, it's incredibly common, and it also has some useful aspects. It's not only pathogenic, it's pathological. It's also useful. For example, cross-linking of collagen occurs upon halogenation. So unfortunately, halogenation is not yet very well known, but there are nowadays many new discoveries about the role of halogenation from the pathological point of view, but also from the useful and natural point of view.
I see. And then mainly, but these are this is naturally happening, or is being influenced for there are more chlorinated compounds around, or it doesn't depend from the outside pollution? It's just naturally we get.
It is natural. It doesn't depend on the pollution. It's just oxidative halogenation, which means by catalase and by peroxidases and hydrogen peroxide plus the chloride and bromide coming from the food, then you get these halogenating species. So it's fully natural.
I see. And which one do you think will be the main therapeutical use where we can find the halogen bonding? Like, do you foresee close an application where we are going to?
Oh yes, I mean there are, yes, absolutely. There are almost 50 to 60% of the new drugs, they are halogenated. So halogenation is used very much in drug design. And nowadays, we have a very big project with many hospitals here in Milan. One of the most powerful drugs for melanoma and the most powerful drugs for kinase inhibitors are iodofluorinated compounds. So yes, definitely drug design is where this halogen bonding is working mostly. And there are several drugs already used in clinics which are iodofluorinated.
Okay, so that's a very, very nice result out of these studies. Yes. So I think, yes, I guess that you have given a very, very clear presentation. And then so far, yes, we are having here, okay. So let's see. Gabby is asking, is congratulating you for this excellent lecture. And he's having a curiosity about how did you crystallize your peptide halogen complexes or lattice gold complex? And can you comment on the crystallization techniques or that you typically use?
Oh, yes. Actually, they are very, very trivial ones. So nothing very special. The point is that introducing halogenidum for the dimensions of the halogenidum, for the atomic weight of the halogenidum, and also for the interaction it gives, somehow we understood that improves a lot the crystallization. So actually, before starting with this kind of works, there were not so many amyloid peptides crystallized. And actually, we are getting nowadays a lot of crystal structure. So we are also using halogenation as a way to get single crystal structure of amyloids because as you may understand, it is important also from the implication that these amyloids have in many pathologies. So I would say really no spatial crystallization technique. So we have just solvent evaporation, and we are typically working in water. We add some non-cosolvent. I mean, nothing very special. Simply, obviously, these crystals are difficult. They are very small. You always need maybe synchrotron radiation. But after all, we have an unusual nowadays number of single crystal structure of amyloids. The fluorinated cluster, I can tell you, it took 6 months crystallization upon slow oxidation from the reduced state to the oxidized state. So in that case, it was more complex, but crystals were very, very many, 10 milligrams of crystals, very huge ones. Obviously, we still needed synchrotron radiation to get the full high resolution crystal structure.
Okay, thank you very much. And then we also have a message from Santiago Alvarez. Thank you for your interesting overview and many congratulations for your achievements. And also there is another question that also congratulates you for the nice talk. And he's wondering about how the halogen ions behave in these intermolecular interactions, if you have done any studies on that.
No, I mean, if you intend the halides, which is I minus and bromide, Br minus and chloride minus, typically those are halogen bond acceptors. So they are very good electron density donor to halogen bond species. I don't know if you intended the alonium ions, which are the I plus species. I plus species are extremely good halogen bond donor. So which one do you?
Okay, we'll ask, okay.
No, okay, chloride and bromide are always electron donor. So no halogen bond donor, but acceptors.
Okay, and then there is another question from Oscar, and then is wondering to check how much is the influence, how far away has to be the electron withdrawing group from the halogen or the chalcogen atom to manage to get a strong sigma hole, basically. Like,
okay.
what is the limit of where we place these kind of withdrawing groups to actually still have a good sigma hole?
Okay, obviously, if it is a conjugated system, it's not a problem. Otherwise, I believe that typically the electron withdrawing residue should be directly attached to the carbon, for example, which is bound to the halogen. So not very far away, not very far. For example, not very far away. If we did a study with fluorination in alpha is okay, fluorination in beta doesn't work much. So either the system is conjugated or the electron withdrawing environment should be very close. Okay.
Okay, thank you very much. And then another question I have, when you were mentioning the interpenetrating structures, that you found a significant difference in between ethanol and methanol in terms of how they were kind of interlocked, the different structures. Did you try different type of solvents, like not alcohols, but maybe a non-polar solvent, or?
So we tried also, yes, I think I remember it was acetonitrile. We tried too, but actually we are always getting this interpenetrated system, but it was really by chance that we got to the methanol polymorph. But this was quite interesting in view of the solid state reaction, because in the solid state reaction, it is amazing that you can control the two polymorphs by simply using different energies in the ball milling. That was our main point. And moreover, they are in clear interconversion, because one is the kinetic form, the other is the thermodynamic one. And moreover, to our surprise, the first complex that forms, it is the neutral one, which is quite less, I would say, stable, but forms very, very soon. And then this consumes, forming the ternary component, the ternary structure. So it was a very, very difficult system to understand, but actually it was very clear.
Yes, no, it's definitely very interesting, the study you did with the milling and to check how the energy influence. That's really, really nice. Okay, so I think we don't have any more questions. So I would like to thank you again very much for for your time and for this fantastic presentation, and to show us how all the potential that halogen bonding has. And I hope that at some point we can welcome you in person when meetings are back to be allowed, hopefully this year or next year. Okay, so thank you very much again, and thank you everybody for attending today to this webinar. So thank you very much.
Thank you very much. It was a pleasure, and definitely would like to meet you all in person soon. Let's hope so. All the best and stay safe.
Okay, thank you.
Thank you very much.
Bye bye.
Thank you.
Ciao,
Bye.
ciao.
Bye. Ciao.